All right, here we go. Okay, let's. I'm hoping to give you a little chance to work today on this stuff. So, quick and close. Let's take a quick look here. So here's what we talked about a bunch of stuff yesterday. Let's quickly just kind of make sure we get back up to speed with where we were. If we're trying to graph a rational function, so we used as our example a polynomial. Right? What do we really need? If we want to graph a function, we need to know the domain. Well, for polynomials, that's easy. It's just all reals, right? We want to know what the end behavior is. For polynomials, we realize that when we're talking about very large values of x, positive or negative, and the tails of the function as x approaches positive or negative infinity, all we got to do is just look at the behavior of the leading term, right? Now our leading term in this case was a negative x to the fourth, but we know negative x to the fourth has end behavior that's going to look like that, right? It's going down to infinity in both tails. And so we're able to add, we never did this, so we got to add that information on our table. The limit as we approach negative infinity is, oh, it's not infinity, is negative infinity. The limit as we approach positive infinity is positive infinity, right? And so we know for our sketch, you know, what that's going to look like at the end, right? We know that we wanted to find the zeros, right? So we factored this thing and we found all the zeros. The zeros were at x equals 0, 6, and 3. And so we know those are going to be x-intercepts, right? And then all we had to do was just check the sign of the function of y in between those zeros to figure out is the function above or below the x-axis, and we just kind of use that information to make a sketch of the curve, right? So it's a little bit tougher with a rational function, but our approach is basically the same, right? If we want to find the end behavior, once again, we're going to look at the leading terms of the top and the bottom. So as x approaches plus or minus infinity, we're just going to look at the ratio of the leading terms. The limit of f of x is just going to be the limit of the leading term on top divided by the leading term on the bottom, right? And in that case, look what happens. I have an x over an x squared, so I could cancel one of the x's and I end up with negative 4 over x. Well, we know that as x gets really big, that fraction is going to go to 0, right? And so we end up with the limits at negative infinity and positive infinity both end up being 0, right? So that tells us we've got a horizontal asymptote again at y equals 0. So let's kind of keep track of all the stuff for this function. So we found out that horizontal asymptote is going to be y equals 0 in this case. We factored the top and the bottom, and we had to figure out what are the values of x that would make the bottom 0 and eliminate those from our domain. Well, the zeros of the bottom are 5 and negative 2. Okay, so we know there's something going on there. What are the only possible things that could be happening at 5 and negative 2 if there's zeros of the denominator? What's one thing that could be happening when we divide by 0? We have 0 at the bottom. I mean, I guess what I'm saying is, what does that result? What are the results of those two values for our graph?
The missing y.
There's a hole.
There could be a hole.
If they're shared, there's a hole. If they're not, then there's an asymptote.
Okay, so there's only two possible things that are happening. One of those two things has to be happening at each of these values. Both of those, each one of those either has to be a hole in the function or it has to be a vertical asymptote, right? How do you know the difference?
If they're shared.
Okay, so if it's a shared 0 of the numerator and the denominator, like 5, then it's a hole. If it's a unique 0 of the denominator, then it's a vertical asymptote. Just that simple, right? So right there, we get some other information. We know that we've got a vertical asymptote, and the equation of the vertical asymptote is x equals negative 2. It's a vertical line at x equals negative 2, okay? We got a hole, and the value of x, where we found our hole, is 5, okay? In calculus, we'll be able to know what's the location of the hole, right? We could probably do it now, but we're not going to bother, right? We just want to know what x value does the hole sit at. And we know our domain, right? We excluded those values from our domain. And I guess that's all, I mean, that's a lot of stuff, right? And then the rest of the stuff that we got, we found by checking the signs of the function of y, or f of x, or whatever you want to call it, between all the important points. But this time, there's a little more to it than just the x-intercepts. With the polynomial, all we needed to do was check between the x-intercepts. For this kind of a function, a rational function, we want to check between the zeros of the function. Now, where would the zeros of f of x be? When does a fraction equal 0? When the top is 0 and the bottom is not, right? 0 divided by 5 is 0, okay? 5 divided by 0 blows up. That's a vertical asymptote. 0 divided by 0 is a whole, right? That's indeterminate, okay? We didn't have any unique zeros of the top. That's how we would describe that. The zeros of the function, meaning the x-intercepts, would be at the unique zeros of the numerator, and there weren't any. So we got no x-intercepts for this function. But there were some other places we still needed to be careful about. Any place where we got a 0 of the bottom, we put that on our chart. -2 ended up being a vertical asymptote, 5 ended up being a whole. We still have to check the value of the function, picking test points that are around and between those. How come? Well, why the vertical asymptote? A vertical asymptote kind of like divides your function into separate universes. And so it could easily happen, and it did in this case, that when we move from one side of a vertical asymptote to the other, the function is going to jump down either above or below the x-axis. You just never know what's going to happen. If you're looking at a vertical asymptote, it completely separates things, right? The behavior is different. So we got to know. We got to check to the left of the vertical asymptote and see is the function above or below the x-axis. You know, is y positive or negative? We got to check to the right of it and see the same thing. Is it above or below the x-axis? Is y positive or negative? And then the other one, and this is a little more subtle, is at the whole. Okay? And you might think, looking at this, you know, why would we have to check the whole? The whole is just one little piece that's missing from the function, so why do we need to check the sign of the function there? Why do you think you might? I mean, in this case, we didn't need to, right? The whole, the function was negative to the left of the whole and negative to the right of the whole. Doesn't it seem like it's always going to be that way? Can you think of any cases where the function might jump across the x-axis at a whole? What do you think? There you go. If the whole would have been an x-intercept, right? Then that could be another place where the function changes sign, right? We could actually, I mean, if we really thought about it, we could have seen in this case that that wasn't going to happen. When do you think, well, I don't want to go off too much of a tangent here. Can anybody quickly tell me what might cause that to happen? That it would have been an x-intercept, but it ends up not being one? Because it's a whole break in space-time. No. What do you think?
I thought you said this test was going to be easier.
Well, I think it would.
I'm lost.
I mean, this is kind of this isn't like something I'm gonna, not really a testable topic, but I just want you to see if you can just use your brains here a little bit and think about how could I get a situation where, how would I know, in this case, the whole was at x equals 5, right? But it was not an x-intercept. Could we get one? What would I have had to have done to this to turn that into an x-intercept, that whole?
-0.
Right. How could it have, in this case, it wasn't a 0. We were able to divide the x minus 5s away to fill the hole, right? I mean, if we create a new function that filled in the hole, all we did was cancel the x minus 5s. And it's a different function, right? But it looks identical. The only difference was it fills in the hole. What do you think?
Another x minus 5.
Ah, there it is. If there's another x minus 5. So if this had been, for example, if this had been x minus 5 squared, right? Then what would have happened when we canceled an x minus 5. We would have had an x minus 5 gone from the bottom and 1 from the top, and it still would have been there, right? So it still would have looked like an x-intercept, right? It would have ended up being a 0 of the top. That would have been a case where it's still a hole, right? Because it's a shared 0 in our function, but the hole in that case would have been on the x-axis, okay? Do you need to probably, I mean, it's just kind of nice to know. And the more when we get to calculus, you'll think about that stuff more probably than you do now, because of the context of what we're doing. But it's kind of nice to think about that, right? For now, though, you could just always play it safe and just check a test value on either side of the hole, right? Just makes it easy, okay? Just be consistent. All right. So let's look at another one. How about this one? And I'm picking these, I just want to do 3 examples, and when we're all done, you'll see why I picked these 3 examples. So let's do the same stuff. This is a pretty quick and easy one, though. So for this function, what's the domain? Are there any values of x we have to exclude?
3i.
Okay, but I, now, where is I on the x-axis? Nowhere, because the x-axis is the real axis, right? So we're looking for real zeros of the denominator and numerator. Are there any real zeros of the denominator? No. Okay, so the domain for us then is all real numbers, right? So we're going to go all the way from negative infinity up to infinity, and there's no values we have to exclude, okay? So if we're keeping track of this stuff, the domain, there it is, all reals, okay? Any zeros of the numerator?
0.
0. Okay, x equals 0. So we could add the value x equals 0. At x equals 0, y equals 0. So there's an ordered pair. And we could add a point to our graph. We know the function goes through the x-axis at x equals 0. Or touches the x-axis at x equals 0. So we don't know if it goes through, but it touches it. Okay, what about, let's look at maybe the end behavior. Let's look at what happens at the extreme values of the function. So as x approaches plus or minus infinity, all we have to do is consider the leading terms on the top and the bottom, right? And so what do we get? Well, the limit of f of x would be the limit of 5x squared over x squared. And that's just 5, isn't it? Right? 5x squared over x squared, that's all just equal to 5. So in the limit, as x approaches negative infinity, y equals 5. As x approaches positive infinity, not x equals 5, y equals 5. And what's the equation for our horizontal asymptote then? Y equals 5, right? If the limit of the function as x approaches plus or minus infinity, so what's y doing? If we go infinitely far to the right or the left, y ends up equaling 5, then our horizontal asymptote is y equals 5.
Oh, where did the 9 go? In the denominator.
Well, if we're considering the end behavior, as x approaches plus or minus infinity, what happens to x squared plus 9?
Okay.
The 9 we can just forget about. All we care about is the leading terms, right? What's going to be the dominant part of the top and the bottom, okay? So we end up with a horizontal asymptote at 5. Whoops, that's a bad, you know what? Those are bad numbers on there. I'm going to change these. We're going to go by 2s. So that's going to be 2, 4, 6, 8, 7. There we go. So there's our horizontal asymptote, y equals 5. Okay, we have no vertical asymptotes. Now, what's this mean again, the horizontal asymptote? What's it mean in terms of what the function looks like?
It never goes there.
Okay, so out there and out there, it's going to stick to that, right? In between, who knows? Okay. There's, you know what though? There's no points to even test on this, are there? We have no zeros of the denominator. Well, the only point we have is at 0. We have 1 to test, right? We have an x-intercept at 0. So what test points might we use?
1.
1 and
Negative one.
Negative one. We just have to have a point between 0 and infinity and a point between 0 and negative infinity. So we could just pick the values, if we want to, we could just pick the values 1 and negative 1. And we just need to know the sign of the function, that's it. So all we have to do is just evaluate the sign, what's f of 1. Well, if I plug 1 in, pretty easy, I mean,
Plus.
positive on the top, positive on the bottom, right? So what's that equal to? Positive, okay? What if I plug negative 1 in? Oh, look, all the x's are being squared, so does it matter if x is negative? No, right? So I end up with the same thing, I'm gonna get positive. And so, what's this function gonna look like? So, in this case, it's gotta touch the x-axis here, it's gotta be above the x-axis here, right? Above the x-axis here. What's it doing? Kind of a boring function. Yeah, it's just kind of going like this, isn't it? It's just kind of going, and then it's going to kind of stick to that thing as we go out to the right.
Broke the line.
Right? That's our function. Okay? That's pretty good, isn't it?
Right.
Here's training. Okay, get the idea? So if we summarize this, vertical asymptotes, none. Holes occur at nowhere, right? Horizontal asymptote, yeah, we did get that. We got y equals 5. Okay, last one. One more example. Let's look at this guy. Okay, wow, yeah. Okay, so let's factor it first of all. What's the bottom factor? That's easy.
Negative 4 and 4 and I don't know.
So we get
4 and negative 2.
4, oh, it's not equals, minus 2.
There you go.
Okay, so then our domain would be what? X cannot equal 2 or negative 4. Okay, we'll keep track of everything. So our domain, 2 and negative 4, is that what it was? Okay, now for us to really go anywhere from there, we need to figure out what's the top factor into. Now that's, unfortunately, that's, well, it's not even gonna group though, is it? Because the ratio of 2 to 10 is not the same as 16 to 24, right? So we'd have to do something like that. Okay, but what we might wanna do here, let's kill two birds with one stone. How about if we try the zeros of the denominator first, right? So let's maybe try like 2, okay? So let's see what happens. If we try 2, if I try 2 out here, what happens?
Can you just test it?
Yeah, 2 is gonna work. We don't wanna do too much of this, too. So I bring the 2 down. 2 times 2 is 4, plus 10 is what? 14, okay, so 14 plus 10 is, oh, that's not gonna work, is it?
No. It's 10 plus 4.
Did that not work?
Don't you bring the 2 down? Don't you bring the 2 down?
So it's 14, 28. Oh, it works, never mind, it works. Yeah, it works. It's gonna work. So 2 times 14 is 28 plus negative 16. 12. 2 times 12 is plus negative 24.
0.
0, what do you know? Okay, so we got 1, and that's really all we need, isn't it? If I can get 1, then I know that the top is going to factor into x minus 2 times, what's that?
Squared.
2x squared
Plus
14x
12.
plus 12. And I guess we were kind of dumb at the start. We could have pulled a 2 out of the whole thing, couldn't we? Right. So what's that factor into? So then we could factor that into, I could take a 2 out of that, right?
You can always pull
Right, so then we end up with,
X squared plus 7x plus 6.
so we end up with the top.
Then it's 1 and
2x cubed plus 10x squared minus 16x minus 24 equals 2 times x minus 2. If I take a 2 out of that, I just get x squared plus 7x plus 6.
1 and 6.
And so that factors into x plus 6 and x plus 1. So I end up with 2 times x minus 2 times x plus 6 times x plus 1. So let's go back and write that. So what was that again? 2 times x minus 2. Okay, so that helps, right? So now, what can you tell me here? Where do I have a hole? At 2, okay? Okay, so at 2, all right, so let's make that a hole. So we at 2, we're gonna have an undefined function, but we know that that's a hole. Where do I have a vertical asymptote?
4. Negative 4.
Negative 4. Okay, so down here at negative 4. I get an undefined function, and that's a vertical asymptote. Okay? Are there any other zeros of the function?
Negative 1, negative 6. Negative 6.
Okay, at negative 1, the function is 0, and at negative 6, the function is 0. So those are x-intercepts, right? So we can add some stuff already to our picture.
Yeah, let's do it.
So we know we've got a point at negative 1, 0. We've got a point at negative 6, 0. I've got a vertical asymptote at negative 4.
Oh, yeah?
Right? Yep.
Are you recording?
Oh, no. I am. Yes. You made me nervous there for a second, but I am. Okay? Okay, so let's just now, how about if we, while we're at it, while we're working with the function here, let's go ahead and check some test points. Where should our test points be?
Probably like 1.
I could do, yeah, but I could do better than 1. What's the easier one between these two? The easiest possible one, 0, okay? At 3, I'm just gonna pick like 4, something a little bigger. In here I could do negative 2. In here, what's probably the one I should pick? And back here, we'll just do negative 10. So we gotta just check the value of the function at those places, right?
So there's gonna be 2 graphs or 2 lines,
What do you mean?
because there's a point on either side of the asymptote.
There's gonna, well, yeah, we gotta check around the asymptote, right?
So it's gonna be 2 lines, right? On that.
I don't understand what you're saying.
Okay, look down. How is that gonna be 1 line if you can't ever touch that line?
Well, it's got, the function has to either bend up or bend down at the asymptote to, to either bend up to positive infinity, right?
So it's 2 separate lines.
We're gonna get two, right, it's gotta separate the function, right, yeah. Okay, so at f of negative 10, what are we gonna get? Let's look at our signs. So I got a positive 2. At negative 10, I get negative times negative times negative divided by what? Negative times negative. So what's that give me then? On the top I get negative, on the bottom I get positive, so the overall sign is
Negative.
negative. Okay, at negative 5, we'll just kind of go through this fast. At negative 5, so if I turn that into a negative 5, what's going to change?
Positive.
This one's going to become positive, isn't it? That guy right there. Everything else stays negative. And that one becomes
Negative.
still negative. Yeah.
Yeah.
Okay. So that makes it positive over positive, which is
Positive.
positive. Okay, what about at -2?
Probably positive. Or maybe not.
So at -2, we're gonna get positive, positive, or negative, positive, negative, positive, right?
Positive.
Negative. So we get positive over negative, agreed?
Negative.
Which is negative.
Positive. Positive.
Was the last one supposed to be positive or?
I think you messed up.
You're not
I think I did too.
I think you're not positive.
I think I did. If I go back, let's go back a little bit.
I think the amount
I
of
should have gotten,
knowledge I'm getting is negative.
did I mess that up?
Yeah, let's learn about black holes.
Hang on a minute. Negative, no, that's right. That's right. I get positive over positive. No, it's right. Okay, I think we're good. And so what about at 0?
My cranium.
At 0, we're gonna get positive, negative, positive, positive,
Yep.
positive, negative. So now we're getting negative over negative, which is positive. And then finally at 4, what's that gonna be? We're gonna get
Positive.
positive,
Positive. 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 Positive.
positive, 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 positive. So it's a pretty positive function there. It's positive.
Right.
Okay, get the idea? Okay, so we know that, but what's the one last thing we're missing? We're missing the end behavior. Okay, I saved the best for the last, so the end behavior.
The end behavior for two of them is gonna be the asymptote.
Okay, you with me? So if we're gonna take the limit as x approaches plus or minus infinity, I guess I didn't put the plus or minus there, but we're checking them both. It's gonna be the ratios of the leading terms, right? So I've got the 2x cubed over the x squared. Well, what does that reduce to?
2x.
2x, right? Okay, so that, as x approaches positive or negative infinity, that's not good. That ends up being infinite, right? If I approach positive infinity, well, 2x is gonna be positive infinity, isn't it? If I put a really big positive number in for x, I get a really big positive number back for y. So I can fill in out here, I guess I didn't put my limits in, did I? So out here, our limit at negative infinity and positive infinity. The limit at positive infinity is positive infinity. What's the limit at negative infinity? If I put a really big negative number in for 2x there,
This is gonna be a really big negative
I'm
number.
gonna get a really big negative number. So the function's gonna go up to infinity at the right and down to negative infinity at the left. Okay, but we can do one better than that. Now think about this function. If I've got a cubic polynomial divided by a quadratic, just think about what would happen if I divided those. What's the result gonna look like? What do you think? I've got an x cubed is the biggest power on top, so it's cubic. X squared on the bottom. If I divide those, I'm gonna end up getting, I know I'm gonna end up getting an x, right? I'm gonna get an x in my answer, and then maybe I get some x plus or minus some number, right? What are you looking at? Is there something weird up there? No, maybe not.
No.
Okay, so I've got an x plus or minus, and it's actually gonna be a 2x, but what I know is it's gonna be the first power of x. I'm gonna get back a line plus some remainder, right? So what happens if we actually divide this out? Okay, we know what the zeros of the denominator are. They're -4 and +2. And so we could just make use of all the work we did here already, right? If we divide this thing out, if I want to divide the top by the bottom, couldn't I just divide the top first by 2, because that's a factor of the bottom, right? And see what I get, and we did, we got an answer, right? We found that if I divide, I'm gonna borrow this. Okay, we got an answer, right? If I divide the top if I divide that by x, what was it, -2, we got that answer. Or we got, what answer did we get? We got that answer,
Yeah.
right? Right there. Okay, so that was equal to that, 2x squared plus 14x plus 12. Right? Okay, so now all I've got to do is I could divide that by the other factor of the bottom to see what's left over, couldn't I? Instead of having to do long division. Does that make sense? Because really I'm just dividing by, instead of dividing by the whole thing, I'm just going to divide by x plus, or x minus 2, which I just did, times x plus 4, right? If I want to divide 12 by, instead of dividing 12 by, or if I want to divide 24 by 6, I could divide it by 2 first and then divide by 3, couldn't I? Make sense? I mean, and we could just divide it out long division. I'm just showing you a shortcut. We could use repetitive synthetic division, right? So if I divide first by 2 and I got a 0, then all I'd have to do now is just do the same process again. Right now, we're just going to start over with this function, and we're going to divide it by -4. Everybody see that?
Yes.
Okay? So what do I get then if I divide by -4? I get 2 times -4 is -8, plus 14 is what? 6. 6 times -4 is -24, plus 12 is -12. So that's my remainder, right? So what did I get? I got 2x plus 6 with a remainder of -12, right? Everybody see that? Okay, you know what? Raise your hand if this is making sense, this last part.
Well, what do you do with the remainder?
Not so well. Okay, I'm gonna bunch that. We'll come back later and when we have more time and we'll look at why that worked. But I don't think this is working very well. I just don't feel like it's. Let's just use long division. Okay, long division. X squared goes into 2x cubed how many times?
1.
2x. I distribute the 2x. 2x cubed
4x squared.
plus 4x squared
minus 16.
minus 16x, right?
Yeah.
Okay, I subtract. So those cancel, end up with 6x squared plus 0x minus 24. X squared goes into 6x squared 6 times. Okay? Multiply through by 6. I'm going to get 6x squared minus 12x minus 48. I'm going to subtract the whole thing. And what's my remainder? Did I mess up?
Plus
Plus 12.
Oh, it's plus 12x. You're right. Okay, so if I subtract the whole thing then, those cancel. 0 minus 12x is minus 12x. Negative 24 minus negative 48 is plus 24, right? So there's my remainder. So my answer is, I'm going to get back 2x plus 6 plus my remainder of negative 12x plus 24 divided by x squared plus 2x minus 8, if I divide it out. Okay, now, what happens if we take the limit of that function as x approaches plus or minus infinity? Well, what's going to happen here? Well, look, I mean, does everybody see that? If I take the limit of this rational function, I got a polynomial, which is easy to deal with, plus I got this remainder, which gave me a rational function, right? If I look at the ratios of the leading terms, we already did one like that. That's the first problem we did, right? If x goes to positive or negative infinity, if I look at the ratio of the leading terms, I could cancel an x, right? What would the ratio of the leading terms become? Minus 12 over x, right? So as x goes to plus or minus infinity, that fraction's going to 0. We don't even have to cancel the x's. This is going to sound a little weird, but as x approaches, let's say, positive infinity or negative, the top is going to infinity, right? Because it's got an x in it. But the bottom is going to infinity infinitely faster because it's got an x times an x. See what I'm saying? Okay, so even though the top is exploding, the bottom is exploding infinitely faster, and so the fraction still gets pushed to 0, right? I mean, but we can cancel the x's and just see that behavior pretty easily right there, right? Okay? But what's left behind then? What's left behind is if this whole thing goes to 0, then the limit of the function as x approaches plus or minus infinity is just, that part goes away. I just get 2x plus 6. What's that look like? That looks like a line, right? So our asymptote in this case is not vertical, or is it not horizontal, right? It's slanted. It looks like a line with a slope of 2. So we call that a slant asymptote. Okay, we get a slant asymptote, and we go back to our chart. And so clear back here. At, what was it, y equals 2x plus 6? Yep. So 2x plus 6 is the, isn't that what, was that what it was?
Yes, it is.
Yes.
I don't understand how you go back one page and it's there, and you gotta go forward 14 pages.
Because it was quite a ways forward. So then if I draw that slant asymptote in there, it's not a very convenient one. There's y-intercept of 6. My slope is 2. So it'd look like this, right? Something like that. There's my slant asymptote. And so the function's got to stick to that at the tails, and it's got to stick to it's got to be separated by this one, right? So now if we look at our information, what do we find?
Isn't that 2x plus 6 what you got with the, when you synthetically divided the other? So could we just do that and find it, or?
What do you mean?
When we divided by negative 4.
Oh, you mean over,
Yeah, right
over
there.
here? Well, yeah, that's what I was trying to show you guys, but I felt like it wasn't really going anywhere, you know?
Well, it worked.
It did. You're right, it did. 2x, so the result of that, next time we look at it, maybe, we'll kind of look back and say, okay, why'd that work, right?
So if there's a remainder there, that's what it is.
Well, even if there's not a remainder, right? If I'm just, I know I'm gonna discard the remainder, right? If I'm trying to find a slant asymptote, okay? So all I really have to do is if the bottom is something that factors easily, I could just use 2 iterations of synthetic division, right?
Is that because-
I know that the zeros of the bottom are 2 and negative 4, so all I have to do is divide the top one by 2. Whatever I get, I do it again and divide by 4, and whatever the linear part of the answer is, that's my slant asymptote, right? If you want to do it that way, to me it's a little quicker.
Yeah, definitely.
But then, if we connect the dots on our function, rather than me trying to graph it, let's just put it up on Desmos and we'll show that it's the same thing.
That's gonna work.
Okay. Yeah. You guys, I think you definitely work day tomorrow.
I appreciate that work.
Hey, no problems.
It is covered in.
You know how many? Well, now you know this one.
Anybody else in the class? Suicide pathways. I can almost see.
Okay, so here's our function. Okay.
Don't cheat like that.
Alright, let's go.
Hey, guys, the bell doesn't dismiss you, the teacher does. Sit down.
There is no bell.
Exactly. Why are you staying?
Alright, we'll wrap this up next week.